So these landmarks are just like dots placed on the important parts of the face. Say, for example, one dot on the corner of the mouth, one dot on the tip of the nose, or at the edges of the eyes or eyebrows. All these are called as facial landmarks. These dots, they're just like dots. So the computer now, what it does, it measures how far these points move or how their positions change when someone makes an expression. So these movements are converted into numbers which the AI can read because the AI understands mathematical language only. So instead of seeing a smile or frown like our what a normal human beings see, AI sees the facial expressions as a pattern of numbers, and it learns that one pattern means happy, another pattern means sad, the other pattern means angry. Like that, it has an understanding. So these facial landmarks help us turn human expressions into data. So this data will be computer like it will be understandable by the computer to analyze. This is about the facial landmarks. So this is the typical workflow. If you see here, there are four main steps: data collection, pre processing, model training, and evaluation. Data collection, where it collects the large, diverse data sets. So, first, we gather thousands of pictures or videos of people showing different emotions like happiness, anger, or sadness. This collection of examples is called as the data set. We call it as the data set. The second process is pre-processing. It aligns the faces, normalize lighting, and augment data. So before using the images, we have to clean and adjust them. So to make sure that all faces are aligned properly, lighting is balanced, and the data looks similar. This step helps the computer focus on expressions instead of distractions like background or lightning like that. And the third step is the model training, so that is feeding the data into the CNN, convolutional neural network. So the computer learns from the data. So we use a special type of program called as a convolutional neural network. So we'll see that in detail now. So this CNN studies the facial patterns and learns what emotions look like. And finally, the evaluation. So the testing the model accuracy and deploy into applications. So finally, we test how the computer has learned. If it can correctly identify emotions in new pictures, it's ready to be used in real life applications like healthcare, education, or marketing, or whatever the application may be. So evaluation is very, very important. So what are the challenges in understanding emotions? Firstly, it is lighting and pose. So the models can fail with poor lighting or non-frontal head poses. The system might not work well if the lighting is too dark or if a person's face is turned away from the camera. Just like how a human struggle to read expressions in poor light, AI also has lighting problems. Second challenge is occlusion. So if someone's face is covered by hands, hair, glasses, or a mask, the system can't clearly see their facial expression. So it makes it hard. The AI very hard to guess what the emotion is. It can't guess the emotion correctly. So that is the second challenge. Thirdly, we have cultural nuance. So people from different cultures may show emotions differently. For example, a polite smile in one culture may mean something else in another. So it also has chances of confusing the AI. And finally, we have the ethical concerns. So it is important to make sure people's privacy is protected and that the system doesn't unfairly favor certain groups. So the data must be handled responsibly and without bias. So ensuring the user privacy and avoiding bias in datasets is also a critical concern. So, and this is the understanding the emotion datasets. So here we see different data sets which is used to teach the computers how to recognize the human emotions from faces. So suppose we have a big photo album. So this data set is like a big photo album where the computer learns the emotions. Like if you see here from this Fed 2013, we have fear, happy, neutral, then CK plus data set. We have thousands of images in that. Then AffectNet data set, and it is the largest data set of faces in the wild with varied lighting. So all these data sets, they are actually used to help the computer understand the different emotions. So different collection of photos. So the scientists, they have used it to build and test the computer programs which can tell what emotion a person is undergoing. So the first one is the FIR 2013, that is the facial expression recognition 2013. So it is a very large collection of small simple grayscale face crops. Why it is used means it is for training the early version of AI emotion detecting computer program, because it's very big. It has around 25,000 photos in that. So it helps the program to learn the basic patterns of emotions like fear, happiness, and neutral. So like it is actually like using small quick flashcards for initial learning. The second example is the CK Plus. It is a concatenate AU coded facial expression database. So it is a smaller in number, but the quality is very high. More controlled set of high quality, high resolution photos taken in a lab setting. It is all taken in a lab setting. So the people are posing different emotions. So because the lighting is perfect and the expressions are clear and deliberate, it is used to make sure the computer program is academically accurate and can clearly distinguish between emotions when the conditions are ideal. So it is we can say it is like using professional photo cameras or professional studios to take photos. From that we are analyzing the emotions. And the third data set is AffectNet. So it is a massive collection of photos where people's faces were captured in the wild, which means the photos were taken from the internet, like from movies, social media. Like it was taken from the a wide range of sources. So why it is used? Because it is in the wild. We have messy real world problems, bad lighting, people look away, they are not looking into the camera, partial expressions, different angles, various skin tones. So due to so many differences, this data set is used to make the computer program robust and practical so that it can work well in the real world, not just a lab. So it is like taking snapshots from everyday photo album to learn how emotions look in real life. So to build a good emotion detecting computer, scientists start simple FED 2013 dataset. Then they went in for high accuracy, perfect conditions, CK plus dataset, and finally real world messiness to make it practical. We have the AffectNet dataset. So these are the widely used datasets. All the datasets are readily available in the Kaggle platform. So this is about the FAIR 2013 dataset, because today I'm going to show a real-time example of FAIR 2013 dataset only. So it has 35,887 images. The image size is 48 cross 48 pixels. The color pace is grayscale, and it has seven classes of emotions, seven types of emotions: happy, sad, angry, fear, surprise, disgust, and neutral. So it is actually used for benchmarking the CNN models. So this is what we're going to see today. So coming about the data set split. So if you see here, this larger portion shows the 70% of the training set. So of the 35,887 photos present in the FAIR 2013 data set, 70% is like that is 7 out of every 10 photos is used for classroom material. So this is like looking at the data over and over again to learn the basic rules, like a pulled back mouth with raised cheek means happy, like that. So repeatedly we train the network, we train our CNN. So 70% of the photos we use, that is 7 out of every 10 photos we use for training. Then coming to validation, 20%. 20% means 2 out of every 10 photo is used for testing the system. Running to see how well it's doing. It's like if it performs poorly, then the programmers tune the settings of the model, like adjusting the focus on different photos or features like that. So the model doesn't learn from this data directly. It is just used to assess. That is like testing. Say for example, you have that 70% of training is like full, like a whole classroom taken class. This 20% like assessing by giving small quizzes. And finally, we have 10%, which is the training data set. That is 1 out of every 10 photo is the final exam. Finally, you're going to test whether the network is differentiating the emotions correctly or not. After the program is completely finished with training and tuning, it is tested on this data only once. Since the model has never seen this data before, the score here gives the True, that is truest, most honest measure of how well it will perform on a unseen data in the real world. So this is how it does. Like it is a final exam graded. Now you're taking class. So from the 70% of the data, you're taking class. Okay. That is you are teaching the network, you're teaching the network. 20% is two out of every photo is taken for validation. While you are learning itself, we give some quizzes to assess whether you have understood properly or not. Like that, 20% of the photos it is used for validating, and finally for testing to check whether your learning is perfect or not, only 10% is done. That is one out of every 10 photo is used for finally grading your network. So this is how it does the data split. Why the splitting is important, why the split is necessary, is for preventing overfitting. Then what is overfitting? So this happens when an AI model memorizes the training data too well, including all its tiny flaws and noise. It scores perfectly on the training data but fails miserably on new data. Like if you have 35,887 data set, the network can understand the emotions from these data set. But when you give some other data set, the network fails. So this is to avoid this only, we go on for overfitting. Then the splitting, we keep like, but that is why we split the data into training, validation, and testing. The splits role, so by keeping the testing set completely separate, then we can see unseen until the very end. We can make sure the program has truly learned the rules of emotion recognition, and finally memorize the, it hasn't just memorized the faces, it can even if given a new data set, your CNN should be able to recognize the emotions. So this is how the data set split works, and why splitting is important. So that is the process. And data labels. So these are the examples of data labels. So if you see here, uh, for a computer to learn anything, every piece of data should be labeled. Since the computer, it cannot actually know what a happy face looks like. Only we are going to teach this, that this is a happy face, this is a sad face. For that, like you have a toddler in your house, you show a picture and say it is a dog, right? Unless and until you teach the toddler, you teach the kid that it is a dog, the kid doesn't know it is a dog. Similarly, your network also, unless and until you teach that this emotion is for happy and this facial expression is for sad, your network doesn't know. For that purpose, data labeling is very, very important. So how data labels work in the data set? So if you see here, we have three groups of face images: happy, sad, and angry. So first, the data, the face photos. So the small face crops in black and white are the raw data being fed to the computer. So the actual expressions in the rows of images often vary. You can see images labeled fear, happy, neutral inside the happy group also. So this variation is a common way to show that the model is often trained on many classes simultaneously. That is, it can analyze all the emotions simultaneously. So these blocks are examples of the data that it might be associated with a particular prediction or task. Then the answer, that is labeling the answer. So we label the data, so that whatever label we are giving is the answer key. So when the computer is training, it sees the photo and label at the same time. So this face is happy, this face is sad, this face is angry, like that. So the computer is being tested. When it sees a new face also, it has to guess it and it has to label itself. So what does the AI do here? AI actually, it trains the data. After training the data, the labels allow the computer to form a connection between the visual features, like the curve of a smile or your eyebrows, changes in your eyebrows, all this. So the corresponding emotions will be analyzed. So the quality, finally, the accuracy will be measured, like the quality and correctness of these human assigned labels are crucial. Now, if a face that looks scared is accidentally labeled happy, then the computer will learn the wrong rule. So this lowers the accuracy in the real world. So it actually it is very important for labeling the correct faces with the correct emotions, like that. So data challenges. So coming, we have imbalanced classes. So that is what we have. The problem is when collecting faces in the world and the wild like AffectNet database. Some emotions are much more common than others. For example, people are happy or neutral far more often than they show disgust or surprise, because there is an imbalance in data. So, what is the impact on the computer? So, if the computer sees thousands of happy faces and only a few hundred disgust faces, so it gets so good at recognize happiness. It can easily recognize happiness, but when the face is slightly disgusted just because happy is the most frequent answer, then this is called biasing the model. Like if you have a student who only studies first three chapters of a book because the teacher said that they are very important questions, then they fail the questions from the last chapter, like that only. If you give thousands of images for happy faces and only few hundreds for disgust faces, then your network will not be able to analyze disgust faces more commonly. So that is the first challenge, that is the imbalanced classes. Second one, as we have already discussed, lighting and noise. Or to the poor quality photos, like when they are too dark, they are too bright, blurry, or harsh shadows, then the CNN actually relies on facial cues like slight wrinkle around the eye or shadow from a fur brow. So if the face is completely hidden in shadow or blown out by bright light, those subtle features, they are lost. So the AI can't detect the emotion correctly. Like it is say for example, like reading a map when half of it is smudged with mud or water. We have poured water on map. You cannot view the map correctly. No. So that is the example of the second challenge, lighting and noise. Third one is occlusion, as we have already discussed. So faces are frequently blocked by common items like sunglasses, hands, scarves, or long hair. The computer can't see the eyes, which are critical for distinguishing fear from surprise or mouth, which is the basis for analyzing the emotion. If you have normally nowadays all girls they use free hair. When you use free hair, half of the facial features are hidden with the hair only. So the main emotions from the eyes and the mouth is blocked. So the hidden parts of the face they destroy the patterns the CNN is looking for. So this is the main problem here, this occlusion. And finally, ambiguity, where the expressions are subtle and mixed emotions, so making the labeling itself subjective, so that is confusing the expressions. So real human expressions are actually messy. Sometimes an expression is subtle or it has a mix of emotions. When humans are hired to label the photos, one person might label it as smirk or neutral, while another person might label it as happy. So these differences making the label subjective and makes it very hard for the computer also to understand it, to learn a consistent truth. Like it is like you give the same question to two different students. One student will write it for 5 pages, the other student will write it for 4 pages. So there is difference, right? So that is ambiguity, difference in expressions. Coming to the steps in pre-processing, so we have firstly, face detection, grayscale, resize, normalize, and augmentation. Pre-processing means cleaning, crop the face from the dull image. So the essential cleaning and preparation task that scientists must perform on all their photos before feeding them to the AI, that is for use for training. That is the CNN. So I'm talking about CNN. So before feeding to the CNN for training, like see, we can think of this as a kitchen preparing, like required to turn the raw ingredients to a perfect meal for the computer. So that is the first step. Then we have grayscale, where we convert one channel to reduce the complexity, making it black and white. Color is complex data, so by changing the face to black and white, we remove all the confusing color information and make the computer focus only on the shapes, lines, and shading, which can actually define the emotion. Third is the resizing, that is standardizing all the images to 48 cross 48 pixels. So standardizing the size means the images might come in all different sizes, big, small, high resolution, low resolution, like that. So this step, no, it makes every single image the exactly the same tiny size, 48 cross 48 pixels, which is necessary because the CNN expects a uniform input size. And the fourth process is normalization. So scale pixel values from 0 to 255 to a 0 to 1 range. So it puts the numbers on the same scale. So remember, the pixels are numbers actually. So black starts from black. 0 stands for black. 255 is for white. See, all the pixel value stands between the 0 to 255. So the normalization changes these numbers to a simple range, which is actually from 0 to 1. It typically ranging between zero point 0.0 and 1.0. So this prevents high numbers from shouting louder than low numbers, making the learning process faster and more stable. And the final process is augmentation. Augmentation is creating new image versions to improve the robustness. So, say to prevent the AI from overfitting, that is from memorizing, the scientists take the existing photos and automatically create new versions. Maybe slightly rotate a face, slightly darken it, or flip it horizontally. So, this artificially increases the data set and makes the AI more robust to variations it will see in the real world. So we can see these steps take messy, varied real world photos and transform them into a standardized, clean numerical input so that the CNN can successfully learn the rules of emotion recognition. Now let us see how the AI converts these into images. So this is the facial detection techniques used. So we have the hair cascades, then we have the Hoji SVMs, very fast, simple. Then we have D library landmarks, MTCNN. We'll see what it is now. So the first one, hair cascade, is quick scan. So this is the oldest and simplest tool. It uses basic black and white feature checks like, is this the area darker than the area next to it? So it is a very fast and simplest to use. And what the disadvantages is, it has high false positives. So it often mistakes other things like windows or patterns for a face. It can't differentiate that and struggles if the face is not looking straight ahead. If the person is turning around, it may get confused. Next one is the HOG plus SVM, that is looking at the direction of edges and small parts of the images, and the SVM support vector machine, which uses that information to classify it. It is better than HAR. The accuracy is good, but it is slower than the super fast HAR method. Then we have the next method, DLAB. So the accuracy. So here the technique not only finds the face but also identifies dozens of specific points on the face, like the corner of the eyes, tip of the nose, and all. So higher accuracy and finds features that it can be used for emotions. So more complex to set up and lower than the HOG. Then finally we have the CNN, that is what we are seeing now. So this is the advanced network to analyze the image in multiple stages, getting more precise with each step. So it has higher accuracy and can reliably find faces even if they are turned or angled, robust to pose. It is actually the a disadvantage is it's computationally very expensive because it requires lot of processing power and time, so which it is actually making it slower and more complex to run. This is about, so we can say the choice of the technique is our own our own requirement. So we say we can choose Har cascade method to accept lower accuracy, but generally we go on for CNNs because for understanding better facial to get high accuracy facial recognition. Then going into data augmentation. Data augmentation is it expands the data set by creating modified versions of the existing images. So this helps the model generalize better and prevent it from memorizing the training data. So it is actually a very clever technique. No, it is actually used during the pre-processing step itself. So we have, suppose we have like you have a student with AI model or a textbook, no, normal textbook with the data. Suppose we consider the textbook as the data set. The student is memorizing the textbook. If you only show them a picture of happy face looking perfectly straight with perfect light, then the student will recognize the happy face if it looks exactly like that from the textbook alone. If you give another picture other than the textbook, then it is not possible, right? So data augmentation is actually the trick of creating many slightly altered versions of the original photos to force the student to truly learn the concept of happiness, not just the single picture. Like whatever we are training, only the trained data it can be classifying. What it has to No, this augmentation is creating slightly generalized versions to make it real world applicable. Make the network, even if some other images are given, the network has to classify whether it is a happy, sad, or any expression. So it means the AI can look at a new, never before seen photo in the real world, maybe taken from a slight angle or dim light. Still, the AI should correctly identify the emotion. Okay, and it is also used for preventing memorizing. If the AI only memorizes the original photos, it will perform perfectly on the training data but fail on new real world data. Augmentation introduces variations that the AI has to deal with during training, making it tougher and smarter. So we have common techniques how we create new data. So first one is rotation, horizontal flipping, zooming, and shifting. So rotation is slightly tilting the image of the few degrees. So this teaches the model to recognize a face even if the person tilts their head slightly. Horizontal flipping is creating a mirror image of the face. So this is particularly useful because a face flipped horizontally is still the same face and emotion. Then we have zooming, slightly zooming in or out on the face. This helps the AI recognize the emotion even if the face is slightly closer or far away in a photo. Then we have shifting, finally shifting. Shifting moves the face up, down, left, right in the same frame. So this teaches the network CNN AI that the face doesn't have to be perfectly centered or to be recognized. So this on the right shows how the programmer tells the computer to perform these actions automatically. It's like writing a recipe that says like take the original photo, rotate it 10 degrees, shift it with height and so and so process. Finally, one original photo will be given, but 10 different images will be generated. That is expanding the data set from one single photo. So this process is actually called as augmentation. So augmenting, yeah, boosting the robustness. See, for example, if you see have one image of the monkey and we have created some more images here. So the image on the right takes only one original face. So one monkey's face is the original one. But following the augmentation, we have created so many monkey faces. So the before image, so this is a single original photo taken from the data set. Okay, the after images are all new variations of the same image created automatically by the augmentation tool, combining all the four techniques like we have seen now, no, rotation, shifting, zooming, cropping, flipping, and all. Through that we have recreated so many monkey faces from the before face. So before image is a single photo. From that we have generated so many photos, right? So why we are doing this? For boosting the robustness. Robustness means resilience. So if it means if the AI is tough and it can handle imperfect situations also, even if you give another entirely different face, like the AI will tell you whether the emotion is happy, sad, or not. So even if you have a little rotated or little out of focus face, the AI will tell you whether it is slightly off center or not. So finally, by training on these many varied examples, the AI learns the fundamental pattern of happy rather than memorizing the only one picture that we have given. So this makes the final emotion detection program much more effective when realizing real world photos or video where faces are rarely perfect, centered, or perfectly correct. So it is about giving the computer a very like very rigorous training of giving a classifying a real life photo. Even if it is a messy photo also, the network has to like analyze and tell you what is the emotion of that particular person. So this CNN model, it will process all these clean augmented images. So how the prepared images enter the CNN? So after all the processing, yes, after all the processing, how does the images are being fed into the CNN? So the computer sees it, as we know, the computer sees it as a 48 cross 48 pixels of numbers. Each image will be taken like that. Then the CNN then takes over and uses a layered approach to extract meaningful features. So first the input layer, which takes it as a grid of numbers. If you see here, yeah, if you see here, we have the image of the koala. Okay, it is given to the network. So we have the input layer. So it has a grid of numbers. So the 48 cross 48 pixels of grayscale values, that will be converted from 0 to 1, 0.0 to 1.0 as the input. So here the network's job starts here. To identify the patterns is these numbers which correspond to emotion. So we have the convolutional layers, then we have the feature hunting. So this is where the actual process happens. The CNN uses many digital magnifying glasses called filters or kernels. So each filter slides across the entire image looking for a specific basic visual cue. So one might specialize in finding the vertical lines like the side of the nose. Another might look upward like the smile. So what is the output here in this process? When a filter successfully finds its cue, it generates a strongly recorded feature map. So deeper layers combine these basic cues to find more complex features like an entire eye or a full fro. Next, we have the pooling process, pooling layers. So after the features are found, the pooling layer shrinks the feature maps. So it simplifies the data, speeds up the processing, and makes the model robust to small shifts in the face position. It only keeps the most important signal found in a small area. Finally, we have the fully connected layers. So finally making the final decision, the classifying decision. So we have the fully connected layers. So they take all the sophisticated complex features identified in the earlier steps. So these layers, no, they act as a final voting mechanism and they combine all the evidence. So like we have found a smile, we have found a wrinkle in the eyes and a raised eyebrow. So so and so emotion is detected like that. So the output will be a probability score for the mixture of all the seven emotional classes. So depending upon the feature extracted, whichever is the highest percentile, then the model is guessing that emotion will be recognized. Whether it is happy for 98%, neutral 2% means the happy 98% will be given as the output. This is what it does. So, as such, we can say this whole process of CNN, like recognizing the emotion, we have the convolution, that is the most mathematical step inside the convolution neural network. So, it identifies the features in the image. So, we have we can take convolution as a digital magnifying glass where it looks in for the specific pattern in a photo, like a diagonal line or a mouth curve. So the process of how convolution is how the CNN systematically searches for that particular pattern. So what will be the ingredient? The original grid of pixels. So we are converting everything into 48 cross 48 pixels. Then we have the filter kernel. So here a small specialized grid of numbers, essentially a digital template which will represent the special feature that the CNN is looking for. Suppose it may be a vertical line or whatever. So this filter is actually the magnifying glass. Then we go on for sliding and multiplying. So the CNN takes the filter, slides it across the entire input image, one small area at a time. So wherever the filter lands, the numbers in the filter are multiplied by the numbers in the corresponding section of the image. So this is the pointwise multiplication. So all the multiplied results are added up to give a single number. So if the filter lands on the part of the image that perfectly matches the pattern it's looking for, that is the vertical line filter lands on the side of the nose. So the resulting will be the sum, resulting sum will be a very high number indicating a strong match of what the emotion is. So finally we get the feature map. So as the filter slides over the entire image, the resulting sums, the numbers generated at each location, are recorded on a new smaller grid called the feature map. So this feature map is a brand new processed image that highlights all the locations where the specific feature, that is the vertical line, was found in the original image. So we can say convolution is a process by which the CNN systematically uses specialized features to search for and extract fundamental visual components from the raw image data, converting the original image into a series of feature maps. That is what is doing. And then so once the convolution operation is complete, the CNN uses the pooling method to simplify the finding. Pooling, we can call it as the data simplifier. That is what we have seen here. Then finally reducing the size and detail, too much detail. If the CNN is looking for a mouth, it doesn't need to know the exact pixel coordinates of the mouth corners. It just needs to know that a strong mouth feature exists in the lower center of the face. Pooling to shrink the feature map, no, it retains only the most critical information, making the network faster. Then we have different types of pooling. We have max pooling, everything like that. So depending upon that, it throws away all the numbers, expect the slightly highest number. Then we have the number representing whatever feature that is being extracted. Finally, we have the robustness, that is the reducing the size and if so the efficiency, to improve the efficiency. And then we the robustness, it is a very key feature coming to when we're coming to pooling. So finally, we can say pooling, no, it is a compression tool. It is a very smart compression tool. It takes the detailed map of where a feature is found and shrinks it down, keeping out only the strongest evidence, which makes the entire AI model faster and much more resilient to the real world applications. So the final prediction from the features to the feelings. So this appears within the CNN after multiple rounds of convolution and pooling have extracted and simplified many complex features. So flattening, that is preparing for the word, the fully connected layers, that will be the jury. Like after the pooling layer, no, the resulting feature maps, they are two-dimensional grids. So to prepare them for the final decision making, the network unveils these grids into a single long vector list of numbers. So this step converts the spatial information into a standard format that the final layers can process. Then we have the fully connected layers. They are very similar to simple layers to the MLP, that is the multi-layer perceptron. So now we are looking for very highly processed abstract features instead of wrong missiles. Then finally we have the output layer, that is the final score. So this is the final layer where one neuron for each emotion. The model is trained to recognize happy, sad, angry, fear, like that, disgust, everything. So the network performs its final calculation and assigns a percentage to each neuron. The emotion corresponding to the neuron with the highest probability is the CNN's final prediction. So, for example, if the happy neuron output is 92%, surprise neuron output is 5%, the model classifies the phase as happy. In essence, the CNN gradually moves from identify simple lines, that is the convolution, to complex features, deep CNN layers, to combine all the evidences, that is the fully connected layers, to arrive at a final confident emotion prediction. So this image introduced the data sets, no, the massive collection of photos, which is used to teach the network what the different emotions look like. It is actually like we can say a very big textbook or very big training album, training the computer with the album of photos. So from that, we from every data set, the thing will be taken. The differential processes will be done. So what we have here, the pipeline is the part one is the data preparation, which is the classroom setup. We have the data sets, that is preventing memorization. No? The entire collection of photo is divided into three distinct groups. We have already seen: training set, validation set, and testing set. So 70% is for training, 20% is for validation, and 10% is for the testing set. That this we have already seen. Next is the pre-processing to clean the detect the faces, convert it to grayscale and resize it and normalize it. Finally, augmenting, creating new pictures from the original image. So like forcing the analog AI to recognize happy even if the there are changes in the original photo. Then we come for feature extraction. So we have the CNN using small filters to slide over the image, looking at uh, lines and edges and create feature maps. And pooling. So the pooling is shrinking the feature maps so to reduce the amount of data and improve the robustness. Finally, stacking. Stacking is repeating the process of four and step 4 and 4 5 to go and for deeper layers. It is just like going from recognizing a line to recognizing an entire facial expression. And the path 3 is the classification, the final decision which you're going to take. We have the fully connected layers. The final features are flattened into a single line of data and passed to the final layers, which weigh all the evidence. It is the analogy. For example, we can take it as the jury's final deliberation, combining all the evidences collected to form a hypothesis. Next, we have the final output here. The network assigns a percentage to each possible emotion like happy, angry, sad, disgust, everything like that. So the highest percentage is the final prediction. So the AI confidently states its best guess for the emotion. So this complete process it actually turns a grid of pixel numbers into a final labeled emotion. This is what it does. So this is what we have seen. So this is about how CNN is used for converting to analyzing the different emotions. So here we were talking about the dataset FER dataset, facial expression recognition dataset 2013. So it is readily available in the Kaggle platform. I will tell you how to how to do the implementation. So we have yeah, so we have here log into your Kaggle. We have all ready-madely available data sets. So if you go in for emotion recognition data sets, all the data sets are available. Then you can take from the directory, you can import the training data, testing data, then you can implement it using the Keras platform. This is what is done. I'll tell you. So finally, your output will be like this. So depending upon the facial expression, the final decision will be taken, whether it is sad, happy, or discussed like that. So we go in for a recap of what we have seen for today's session. So we know what why emotion matters and the core psychological concepts we have seen. Then the data sets we have seen about the different data sets and how CNN is being implemented, and finally the challenges. So getting the data ready, that is a pre-processing, phase finding, detection, then cleaning the images, then the augmentation process. Then finally, we have the learning CNN network, so which is the core tool which teaches the computer to see and classify the emotion. So we have the feature extraction, that is breaking the image to important features. From that, we taken for the convolution and the pooling processes. Finally, taking the decision. And third, the third process is the real world use testing and the real world use. This is how it is done. So, key takeaways we have today's session psychology plus AI we have seen, and then how we are going to take the data set, how CNN is used, and finally, real world exam use. So, project ideas we have multimodal recognition, so affective robotics, so building robots that can change the behavior like color of LED based on the person's expression. Then we have multimodal recognition, also creating a more accurate emotion detector by combining facial cues with speech tone. Student mood monitor, like developing tools to ethically monitor students engagement or confusion during online class. And then we have data dimensions, data and the machine's blueprint. So it will tell you, like you can tell the size and shape of the models it is working with. Then we have the student monitor, like develops a e-learning tool which is using a webcam to monitor the student engagement or confusion during online classes. So this is how it does. And finally we have this implementation part. I'll show you how the process is taking place. Mm. So I'm using the Google Colab platform only. So you take a new node, you go into Google Colab with your login. You go in for a new notebook. So I have implemented you. Oh my God. Already I have implemented using this emotion. I have implemented the process and I have saved my notebook as emotion. So I am opening my already saved notebook only. So if you want to run it again, you go on for a new notebook, you open a new notebook, and first you have to upload the data set. If you see here this in this corner, you have a symbol, file symbol like this. From there, you have to go here and upload the data set. So wherever you save, you have saved the data set. If you see here, that FER data set, I've already downloaded and I have saved it in my computer. From that, I'm uploading, or otherwise from the Google Drive also you can mount. Yes. Okay, it is being uploaded. After uploading our data, so it should be a CSV file only, because it cannot be a normal Excel file. So the data set should be in the CSV, comma separated value format like this. So my FER 2013 data set is uploaded. So go to the runtime and select for GPU. So I've already selected this GPU. Otherwise, it will be in CPU mode. We have to change it for T4